Okay, everyone. Welcome back to the next lecture here in theory plasticity. As you saw, I sent out some slides for today, and I had some trouble actually with the equations. There was some line missing again, but I hope I get it right for you this time. Else, you can ask me, and I try to make a new one. So I hope this one works. I also changed to PDF this time because I think it's more stable than the PPT. Of course, there were some strange signs also on the last lecture we had. Okay, today we're going to talk about elasticity and different kind of models. So elasticity of solids, more or less, is the subject of today. And if you look at the outline, first a little bit general about elastic material, then the strain and complementary strain energy, which you can base your models on. Then we have the simplest type of elasticity, the hyperelasticity model. After just going through the first fundamental things with those models, with the first model, we go into the constitutive elastic relations, how you can relate it to a material. And also the next is the reduction of the system, because these systems with the tensor, they grow when you have a lot of parameters, but if you look at how material actually works, you can reduce them quite much. Then we go into a little bit more general elastic model called the Cauchy elasticity model. Then we have these viscoelastic types where you have time dependency of your material, and then we end up with the hypoelasticity model. So as the last time, this will cover more or less chapter 4 and 7 in the course book. And of course, I will not be able to cover everything, so you need to read the book yourself. And that's the main thing with the course. How is it with you? Have you all got the books yet, or anyone have the book? Okay, that's good. It's good that you read it and go through it. Okay, elasticity, what is that then? It's when you deform something, linearly or non-linearly, without permanently deforming it. This is a typical example. This is a non-linear response on a material. And in this one, you also follow back in the same path. So it's the first very, very simple model. The hyperelastic model, which is the absolutely simplest one that you can use. And one thing with that model is that the elastic response is independent of the load path. You always follow back the same way. But you can have it both linear and non-linear. So it's a quite simple one. I will show you a little bit more about that later on. But first you need to know a little bit about what is strain energy. Strain energy, you can look for this picture, for example, that you have in the book, figure 4.2. The strain energy of a deforming process is the area under this curve here. You can also write it in an incremental form, like this one. Then you can take steps and integrate each time. So you can just take a small step here and look at how much energy, elastic energy you have for each step that I take. And strain energy is measured in unit volume. And it's also measurable. Usually measure that in an experiment or something for some kind of process. Another thing that is very important is that the strain energy is an invariant. So if you change your coordinate system, it doesn't matter. It's always the same, and it's as it should be. If you look a little bit more careful about it, you can say that the strain energy is dependent on the strain, how much strain you put into the system. And if you differentiate that relation, you get this one here. And you also know that this term here is the, as we said in the first slide, it's the stress in the system here. So then you can put up this relation here, like this, and put it to 0. And for an hyperelastic material, the most simplest law that you have for elasticity, you can find your stress tensor from taking the derivative of the strain energy, like this. So you can directly find this value in this model. Then you have something else which is maybe a little bit more strange and more difficult to understand. This is complementary energy in the system, which is the stress times the strain minus your strain energy. This will give you the complementary, and it's also measured per unit volume. So if you differentiate this relation here, you will have something like this. And you will see that when you develop this one, it's also described in the book, this one here, you will have this relation. So this one will be left, because you know that this was the stress that you had in the system. So that one will be left. So you have this relation here in the end. So you have a on the opposite that you had for the strain energy. This is the strain are dependent on the stresses instead. So it's the opposite thing. It's the complementary energy. And if you look at the graph, what it really is, if you remember the first response we had for the hyperelastic model, it looked like this. And the strain energy was under the curve, but above the curve you have the complementary energy. So that's why you have this relation. And if you take this integral, you actually take the integral from 0 to the point where you are in stress for the moment. You will find the complementary energy at that point. It's not path dependent, it's variable at all. So if you do that, you will find this relation here, and you can quickly look at this ratio here between C and dC and epsilon, and this one will be sigma 0. This means that the complementary energy is only dependent on the stress that you have in the system. So this means then that this relation is valid. And on the opposite way, taking the differentiation between the C and the sigma, you will find your strain and strain tensor. For the strain energy, you find the stress vector. Here you find the strain vector. You can find them both with putting up this kind of system. So how about elastic solids then? Actually, this theory was developed by Hooke quite early, in 1678, and it's called Hooke's law. Everyone knows that from fundamental solid mechanics courses. And you have a relation between the stresses and the strain. And the thing that keeps it together is the elastic modulus. But if we then assume that there exists an elastic potential, W, which we know is the elastic strain energy, it should be independent of the coordinate transformation. It's the same all over the system. Doesn't matter how you rotate your system. And then you have a system like this. You take a Taylor expansion of that one. You will have an equation looking more or less like this. So you see here is the higher terms, and you have higher ranks of your tensors. So you can develop it as much as you want, but usually these nonlinear terms doesn't matter. And we know that we are working with small deformation, a small strain tensor in this case. So we can just use the first one. So if you just make a small change in the energy, strain energy in the system, we can use this term here, the first one exactly, because we know that the influence of the higher order will not be much. And you know that looking at these curves that you have above here, I can go back to that one. We have the stresses and we have the strains, and we build up the complementary energy and the strain energy. So if we just take a small change in the energy of the system, like this, we keep that one constant and change this one, so we have a small change in the energy. And also from how we develop the strain energy, we know that this criteria is valid, and we make a small change in that system, delta, epsilon. You can see if this should be valid, this system that you have here, this must be true. So this is another way of showing how this works. You had it also for the development of the strain energy, where you got the stress tensor from this relation here. So I just want to show you another way than the book is working. So you can go both ways. So we know that this one works, but we want to make a more general assumption, and so we have a constitutive relation between stresses and strains in the system. You had this Taylor development that I showed you. You can do it for many higher orders also. But if you just look at this one here, this is what we called the general constitutive equation for 3D solids. It covers everything for elasticity. And this term here, dij, is the residual stress that you have in the system. So usually when you're working with programming, you take this term away, or you can put it there if you know that you have residual stresses in your system. This is more or less like a starting stress tensor for the system. But usually when you show it in theory, you put it to zero and assume that you don't have any residual stresses. And also, if you just want to work in this course, we only work with small strains just to make it more easier actually to understand the model. We can skip the higher order terms, this one. So we only work with that one here. So we get a quite nice expression. This is the stiffness tensor. We call it that one. And gives you the relation between the stress tensor and the strain tensor. You will see it more in the continuation of the work, of this work. When you also use plasticity, you need to work with this part especially and split it into elastic and plastic parts. So I will show you the technique for that one later on. So, but we should have some coupling also more than we have seen before between strain energy and the constitutive relations. We know that we can rewrite this one now like this. We can find the strain energy by taking this relation. But this is only valid then for elastic material, linear elastic material. So half of the energy that you see in the graph is the strain energy. The other part is the complementary energy. So it's just a straight line in this case. So you can also write it like this. But you know that energy is always positive in this system. You don't have negative energy for the system. So this is one criteria that you have to fulfill in in your model. So you can simply change it back. You can look at in the other direction, use the complementary energy instead. So then you can use this tensor here. It's called the flexibility tensor, elastic flexibility tensor, C. This will also be used. This is all plastic. If you have plastic response, you will also see how we will work with that later on and split it into two parts. But if you have, for this special case, linear hyperelastic material, you can say that because you divide the energy, you have a straight line and you will divide energy straight off. You can say that C and W is the same. And now we can use this relation to, we can manipulate a little bit this relation here. You know that this should be positive also, all the time. So then you can rewrite, you know that C and W is the same, then you can say that this relation is also larger than 0 for the system. And you can find that your stress tensor have this relation. Now you have the stiffness tensor and the flexibility tensor together with this stress tensor in another system. So this should be the same. You do this transformation. And here you have something. Another way of writing the stress tensor is like this. You use the Kronecker delta. Then it's just like a transformation. It's a mathematical trick that you can use. If you get stuck sometimes in the equation, use this relation here and you will see how it works. But here we use this one and we change that. Instead of writing the stress tensor, we put it in the equation like this, minus the stiffness tensor and the flexibility tensor, and we take this one outside. And it's all together is equal to 0. Then you can write the combination of the stiffness tensor and the flexibility tensor like this. And you can also, you see here, you can change it the other way around. Then you can see, you can prove, as this one is true and this one is true, they should be inverse of each other. This is true only for when you have the relation with the linear elastic material. So this is good to know, and it's also one thing that you can check when you're doing some models. You should check this property if you have linear elastic material. This is a way of checking that your equations are correct. So if we then go back to this general case of elastic relations, we know that we can write the stress tensor like this, but now we have 3D solids. So we have 3, and we have rank 4 tensor here. We have 4 indexes on this one, meaning that you have 3 to the power of 4 is 81 constant, elastic constant. How should you measure that on a material? It should be quite complicated to do that. It's a nightmare, I think. But you know that, as we talked about the last time also, that you have something called symmetry. And you see here on the stress tensor, it's symmetric. And it's also the same case for the elastic tensor. By doing this, you can reduce the number of constants to 36. It's still not good, but it's much better to get rid of a lot of constants. Then if you look at the stiffness tensor for the system, you have something called the major symmetry. If you look at these indexes here, you have IJ, KM, should be the same as KM, IJ. The 2 first are changing place with the 2 last ones. So it's the major symmetry. By doing that, you have 21 constants instead. Now we have a material. Is this right word? Now we have something called a totally anisotropic material. And this tensor looks like this. You have a lot of indexes here, quite complicated. Usually we have this, we write it like this instead. It's enough, I think. We still know what we're meaning. So you don't have to write out all these indexes. It looks a little bit easier when you have it like this. Are you following me with this, how you should think when you have this full tensor with all these constants, and then you reduce it because you have symmetry in different parts of the tensor. It's good if you read in the book also how to think about this, how you can reduce your. So it's not so complex, all these tensors and so on. You use symmetries and planes and so on to make it easier and reduce all these constants. Okay, 21 is still quite much. It's very difficult to measure. So to reduce it more, we can take a material that is monotropic. This means that you have one symmetry plane inside the material. You have the same properties on both sides. It's a symmetry plane. And if you look at A, which is the transformation matrix, which you use for coordinate transformation, it can look like this. You have the difference is you have a -1 here. This means that you have one plane that is a symmetric plane. And if you do this transformation, you will see that some of these positions will be the opposite. It's not symmetric. So for example, you have to do this transformation here. And if you do that, you will have sigma prime 1, 3, you have the negative value here. So it's not symmetric. And also on this position, 2, 3, it's unsymmetric. And also for the elastic, for the strains, you will have 1, 3, and 2, 3. It will be the opposite. But for the rest of the positions, it will be exactly the same. So there you have the symmetry. This is if you do then this calculation on we take out one segment of equations in this full system that you have here. So looking at this sigma 1, 1, it will be like this. You have D11, E11, D12, E22, and so on. And you write it out, all the 6 positions that you have. And then you do the same for the transformed system. You will see, okay, D11, D12, and so on. But here you have minus sign. Okay, it's not the same, you see here. That position and that position, this position and this position, it's not the same. So that means that D15, D16, they have to be 0. That's the only solution to get the system to work. So get rid of those. This will be 0 in the system. Then the transformation will work. And also this was just for one position, 1, 1 in the system. So you have more. You have 1, 2, 3, 4, 5, 6, 7 positions more that you have to check. But as you know what, they always follow in the same manner as you did for the first evaluation of the position. These will be minus, so you will have the same problem at these positions here also. So they also have to be 0. So then we'll put in a lot of zeros in this stiffness tensor. And this will reduce a lot the constant. Okay. We make a new reduction. Now we have 2 symmetric planes. So in your material, you have around 2 planes, symmetric properties, mechanical properties of the material. So we have get rid of We have already get rid of all these positions in the stiffness tensor. Now we have these left. We do the same just to check. Take one position in your evaluation of the stress, and you can see now we have 4 positions left. And when you compare for the original configuration and the transformed configuration, you will see that you have a minus sign in the last position here, and you have a plus sign here. So this means that D14 is 0, and if you take and calculate on all the other positions in your tensor, you will see that 2, 4, 3, 4, 5, 6 have to be 0, else your transformation will not work. So this is a way of reducing the tensor properties to make it more simple. So now we reduce it down to a fully isotropic material instead. So you know what that means. The properties are identical in all the directions. This is the simplest way of thinking. Usually, it's the usual one that you have, for example, for steel. You approximate it, even if you have some differences in the different directions. You can usually approximate like an isotropic material, and it's the easiest way of calculating. And if you look there in the full tensor, you look at the positions D111, D1122, 1133. You will have these properties. Lambda plus 2, I forgot the name. Thanks. And then you can write it like this. You can change it. This is just a simple change here. Because you know these are equal, you can just write it like this. And from this evaluation, you can, if you look at the full properties of the stress tensor like this, you have this lambda, epsilon kk, Kronecker delta, and you have these 2 times mu, and the strain tensor. And this is a very important constitutive relation. And you have this lambda and mu, which are called the Lane parameters, which are these relations for the elastic variables. This is the Poisson ratio, this is the Young's modulus, and you can build up a relation for this Lane parameters. But it's very difficult to measure these properties, these parameters from an experiment. So you need to have other relations. And if you look at material testing, the Young's modulus, quite easy, it's in one dimension, it's the difference, the ratio between the stresses and the strains. It's a very usual one. Poisson ratio is the contraction. If you stretch a material, we'll look at in the orthogonal direction, you see how much it will shrink. So then you have the Poisson ratio. This is measurable also. The bulk modulus is like a 3D Young's modulus, I would say. You look at the volumetric change for a load. So this is the pressure, and this is the trace of the stress tensor. This can be written as K, which is the bulk modulus, and the trace of the strain tensor. And in the end give you this relation, that you have the bulk modulus is the same as minus the pressure divided by the trace of your strain tensor. Another way of writing it is like this. So if you find, for example, Young's modulus for a material and Poisson ratio, you know it's an isotropic material. With this relation, you can find the bulk modulus. And you have other ways also. You also have something called the shear modulus, which is sharing. When you share material, shear test, for example, you can find it from measurement. And this is exactly then the same as this mu. So the most important variables that you have for a material with that isotropy is Young's modulus, Poisson ratio, bulk modulus, and shear modulus. I would say that usually shear modulus can be the most difficult one to measure. But the other three here, usually it's quite easy. And you look at the mathematical framework here and do analyze of stability of the material model. You know that the energy has to be positive and so on. And you can put relations. It's more about that in the book also. For example, that the bulk modulus have to be positive. Also, mu, which is the same as the shear modulus, has to be positive. And also the Young's modulus. This is from, if you look at the energy in the system, it has to be positive all the way. You can find this relation, find this also this criteria for the different parameters by using this relation. Okay. I don't think there exists. Do you know? Anyone know? No, it shouldn't. So it's like a logic. It's a logical thing to. Yeah. Yeah. That's very strange. Especially if you only look at maybe something can happen when you have thermomechanical things going on in a material. There are phase changes and so on. But if you have iso temperature, no way. But it's also a way you have to think like this. You have a mathematical framework. You can do these tensors. You can do anything with them. You have to restrict them, and the way of restricting them is to use logic expressions, like for example, Young's modulus should be positive. That's a very smart way of working with mathematics. Because we can do everything with these tensors. We can show if you want to show negative things, it's possible. But to make it work and connect it to reality, you have to work like this. But it's a good thinking. So, okay, we know about this relation now. You have the stress tensor, stiffness tensor, and elastic strain tensor. Also you can write this like this. Usually you see this in books, for example, that you have the stiffness tensor. You put 2 times the shear modulus, and this relation you remember from the derivation we did before when we rewrite the tensor, but with the Kronecker delta mathematics here. You also put in this Poisson ratio like this, and also with Kronecker delta. This Kronecker delta is more or less to spread out the components in a correct way in the matrix. If you take it indexly exactly the right way it should be, you will find that this relation holds, and you will have a matrix more or less created from this relation. So that's why you have this Kronecker delta spread out in the equation. And this is called the elastic isotropic stiffness tensor. So it's only working for isotropic material. It's not fully general. And the good thing with this one is it's symmetric. So and also that is one logical thing. If you have an isotropic material, it doesn't matter how you rotate it. It should be the same all over. This is what it says mathematically. And you can also write it. Another way of writing it is to put in the strain tensor in this position here. One thing that we use in modeling, mathematical modeling of material, is to split into hydrostatic part and deviatoric part for the stress tensor. And this is this is the trace, and you know that you have a connection there with the bulk modulus. So if you have a volumetric change in your system, you can directly calculate from knowing the bulk modulus, you can find the trace of the stress tensor. That is a good thing. And also you can find the full deviatoric stress tensor by taking the difference, taking away the trace of your stress tensor with this relation. You will directly find, as you saw also in the lecture notes last time, I showed you that this relation is true. So if you look at this relation, then you can write the deviatoric stress tensor like this. But you see here, even simpler, that you have, instead of going through all these equations that you have here, just take 2 times the shear modulus and the deviatoric strain tensor. Then you have it directly. This is usually what you do when you're programming this kind of relation. You know these equations, can from these G's and K, bulk modulus and shear modulus, these material properties that you put into the system. Then you use your strain in the system, for example, or the stresses. Usually we go by the strain because you change the loading. Maybe you put on displacement in your model, and then you recalculate this displacement, the strain, and you know the shear modulus, for example. Then you will have your deviatoric stress tensor from this relation. So elastically, this is quite easy to do, even mathematically, because it's a straight relation. You can almost get it directly, because you don't need, and if you have a hyperelastic material, you can go to that point directly. You don't need to do it incrementally. But if you have plasticity, for example, then you have to do it incrementally, because then you have to divide it into elastic and plastic, and you have to know how much elastic and how much plastic is this increment giving me. But we come into that later. But right now it's quite easy to get the stresses and the strains. And if you remember, the deviatoric strain tensor here can also be written like this. Now we go the other way around. We want to find the strains. We can go by the stresses, stress tensors, and the trace of that one. Using the shear modulus like this. Then we use this relation again, this mathematical trick to rewrite the stress tensor. And this one, the trace here, we can rewrite like with the Kronecker delta from the full tensor. We will find this relation, and you recognize it again, I guess, because this is the ordinary strain tensor. This is the elastic isotropic flexibility tensor, because we have an isotropic material, and this is the stress tensor. And now, we had the relation for your stiffness tensor. We can find the relation for the flexibility tensor. And it's written like this. Now it's 1 divided by 2g, and then you have this. This comes from how you rewrite the stress tensor, and this is just Poisson ratio that you have written like in this form. And you use the Kronecker delta here to spread out your how to build up the matrix for the isotropic system. And also, if you have isotropic material, elastic isotropic, this flexibility tensor will also, it will be the same. If you rotate your material, it will be the same. It doesn't matter. So, this elastic stiffness tensor then, we know that it is a positive definite. This is something you can check also in your calculations later on when you're working with it. In the book you have equation 4.24 and 4.25 looking like this. It was the strain energy that you could find for an linear elastic material. And it also says that the energy is positive all over the system. This is something that has to be fulfilled for this to be working. But if you now look, we had some restriction already on Young's modulus and Poisson ratio. But can we get something more out from it? So if you remember, you can write the strain tensor like this, using the deviatoric strain tensor plus putting on the trace in the system. Calculate that one and set it into the tensor itself. And also the same for the stress tensor part. You are using the deviatoric part This is a way of rewriting your equation. This is just a relation that holds. Now, if we want to express this strain energy in the system with a deviatoric part, we use this equation and put it here. It will look like this. And we know that it's a positive one. That's why I have this. And from the relation above, we could find that one and that one. This is the volumetric part, and this is the deviatoric part. We also connect the shear tensor and the bulk modulus here. So if you go back in the equation, you know you can write it like this. It should also be positive. Looking at the deviatoric strain tensors, they must be positive also in this case. This is also true for the ordinary strain tensor. And this relation, if you evaluate it even more, you can get the rate. You know that these ones are valid, but the last one we were looking at, that we didn't look at, was the Poisson ratio. But this positive definite and the energy that should be positive all over this framework gives you that the Poisson ratio cannot have to vary between -1 to 1/2. So this is restricting your equations even more. And you can, there are also more, read in the book, you can also go further into restricting all these ones even further. I think it's time for a break. So 5 minutes. Okay, I'm back again. So, do you have any questions on the first part here? It's quite mathematical, and I know it's just looking at the presentation. It's not so easy. You need to read the book also and try. This is more like a guideline, and if you have any questions regarding this, you can come to me and we can discuss. And it doesn't. It's not so bad as it looks like. So it can be difficult sometimes, but if you take it step by step, it's quite easy. So. Okay. Before we continue, I want to say we were restricting things because we had the symmetry planes and the material. We have isotropic material, but you can also simplify things with dependent on the kind of the loading that you have. And this is one example, plane strain. Do everyone know what plane strain is? All the strains are in one plane. So if you look at this, this says that out of plane strains, this is epsilon 3,3, the volumetric part, epsilon 1,3, epsilon 2,3. These are out of your plane. If you have a long rod, for example, and you load it in the same manner, and you cut it in the middle, for example, you have only strains in that plane, and all the planes that are exactly the same in the rod. You don't have any strains going out of that plane. That means that's a simplification, a mathematical simplification that you have. And you have these kind of loadings in experiments and so on. And then you can simplify. You see, this reduces your stress tensor. You only have three positions, two shear components, and two volumetric components, and one shear component. And this is the same also with the strain tensor. So if you have that, you have to reduce your stiffness tensor like this. It's much simpler now. It's a 3 times 3 positions in the tensor. And you can also, but something that you have is that you have an out of plane stress, sigma 3,3. This is what you have here. You can calculate that with this relation here. So this is something that comes outside this tensor here. So then you can have an extra one, a volumetric change out of the plane. And you can find it from this relation. The other ones, 1, 3, 2, 3 in the stress tensor, these positions are 0. So this is one thing that you should look into. And also, sometimes in the modeling, it's easier to simplify a model. For example, you use 1D, one dimension. You have just one position. Make the model, try to make it work for 1D. Then you change it, made it to plane strain or plane stress, which is the next slide I will show you. Before you go into a full 3D model, if you usually go into a full 3D model, you have a lot of problems. You have also problem with evaluating things and calculating things. So I usually start with 1D and make it work there, and then I expand my model. It's much easier to do that. So the next case, plane stress, isotropic. Then you have this relation. You have the strains connected with the flexibility tensor to the stress tensor. Here you also have three positions in the stress tensor and in the strain tensor, and it's called plane stress. So this means that all the stresses are in one plane. And it also means that usually you have a very, very thin material in that case. For example, a tensile test with a very, very thin specimen. You can have a plane stress condition. And it's also simplification. You see here that all the out-of-plane stresses, sigma 3,3, sigma 1,3, sigma 2,3,0, and also you can reduce the flexibility tensor to this type here, but you have an out-of-plane strain. So you can calculate that one outside your ordinary calculation with the tensors. You can find it from this relation directly. So this is something you can study, and also when in the modeling, try to think as simple as possible. 1D and then expand 2D and 3D. Okay, Cauchy elasticity. This is a little bit more general assumption for the stresses. You don't necessarily have a independent load history, because it will be surely that you can take care of these problems with having different kind of load packs for your material. Because some material respond differently, for example, with unloading and unloading and loading, and you go backwards and forwards in different directions depending on how it's deformed and so on. And you can have also a combination of different loads. You can have volumetric and maybe a part of shearing in your loading, and then you will have another kind of response elastically. So usually you can write it, in the book they write it like this, that you have the strain tensor is calculated with its G dependent on the stress tensor. And in the book they call it response function. And it's dependent on the stress tensor, as you can see in the equation above here. And it can be different from different coordinate system. So then you put a star on the G, meaning this is a transformed strain. The strains are always calculated in a different way because you rotate your system, and then you will have different measures because you change the coordinate system. So the measure goes to the coordinate system, but the material, if it's isotropic, it will not change at all. It will be the same. And also Hooke's law here is exactly the same as you have seen before. But if you remember, if you are going to transform one tensor, and this is a 4-rank tensor, you can calculate it by the indices. This is 4 indices, so it's a 4-rank tensor. Then you need 4 transformation matrices, like this, AA, C, AA again. Then you have transformed it. But remember from the previous result that if it is an isotropic material, and this is a logical thing, it doesn't matter how you rotate your material. It should be the same. If I have this piece of material and I'm measuring in this direction, and now I just change it, nothing happens. So it's like a logical assumption. It should be also valid for the mathematics. So then you don't need, you can do this transformation and it should be the same. But if you know that it's isotropic, you don't need, because it's always the same. But still, as I told you, this strain tensor, you need to transform it because it's another thing. Even if the material is isotropic, the strain and the stresses are measured in the coordinate system that you work in. So that is important. You always need to transform those properties. And if you look at this relation, you have transformed your strain tensor into another system. Then you have this G star, okay? But it's dependent on the elastic, this strain tensor. So you need to transform this property also. So if you do that on the result from, because you have on the other slide here, you had you have this property here. You transformed it, and then you take this measure here. You can transform your G tensor also because it's dependent on the stresses and the strains. So you will have this relation here, but you have a coordinate invariant for isotropic material also. So that means that the material response is independent of the coordinate system. It's exactly what I said. If you rotate it in the system, it doesn't matter. The material is the same. The only thing that changes is how you measure your strain and your stress. So this, in the book they have this figure. You can check it out and read this quite carefully. You have the response function, which is this G. And if the material is isotropic, you know that if you change the measure, but you have the same loading in the material as you have here, for example, sigma ij for the first coordinate system and for the second coordinate system should be the same. And if the material is isotropic, the strain should also respond in the same manner. So also the strain measured in one coordinate system and the other one, this relation should be the same, which gives you that this response function G and G star, which is for the other position, is also the same. But this is only valid for the isotropic material. If you for example have an anisotropic material where you have different properties in different directions, it's not valid. So that you have to think about. But this coordinate transfer, what you have here, coordinate invariance principle is still valid, but the difference is that this response function is also changing with the position. It's a bit tricky, this one, especially when it comes to the anisotropy, but I think it's quite well described in the book also, so check that out. Okay, now we're going into a little bit more advanced models called the viscoelastic Maxwell model. And viscoelasticity is when you have time-dependent response. And here you can split the tensor, stress tensor here into elastic part and also to an viscous part. So here, that's written here, E is the elastic and V is the viscous part. And you also have a time derivative. This will give you, this relation E dot is the rate of the strain that you have in the system. And this eta is the viscosity coefficient. It's measured by Pascal per second, Pascal times second. And if we put up this system, and we have a split on this strain, the rate of the strain, also into elastic and viscous part. But for the Maxwell model, we know that the elastic and the viscous part is exactly the same. It looks like this one. You have a spring and a dashpot, a damper in the system, meaning that the response, if you load this model, you will have an instant response to the position, and then you have a time-dependent response like this. You have an angle here with sigma divided by eta. So it's a time-dependent change in the system. The model looks like this, and to find the real response on the strains, you need to do an integration of the system. And if you do that, you integrate this rate part. And you can write it like this: sigma divided by the Young's modulus of the system plus sigma plus the time divided by the theta. So this is something that you see usually in some of the first courses in solid mechanics. But you can generalize this with tensors, because we like tensors, of course. So you have a rate tensor, and you divide that one in the same manner, exactly in the same manner. You just put the indexes on here. So you can have it as a full 3D model, plane stress or whatever you want to have. But you need to calculate first the elastic part in the model, and then the viscous. And then you have, in the book, you have this relation for the elastic part. You have alpha times Kronecker delta, alpha 2 times the stress tensor, alpha 3, and then you have 2 times the stress tensor. And if you do that evaluation, you can relate this alpha 1 here, will give you can write that one actually as the elastic properties of the system. The Poisson ratio and the shear modulus here, you can find this relation, times the trace. So this alpha 1 will take care of the hydrostatic stresses in the system. This is the response for the hydrostatic part. Alpha 2 will give you the shearing part, how the material will shear. And you can also find properties for alpha 3, but it's higher order, and we are working with small strains. We skip that one, we put it to 0. So the elastic part, if you do this kind of you splitting with the alpha 1 and alpha 2, you will have this response. And for the viscous part, it's the same expansion actually, but now we have beta 1, beta 2, beta 3. And in the book they do it like this. They have the response on the hydrostatic part, like this, and this will be the shearing part of the system. So, and beta 3 is 0 because it's higher order also. I think they have in the book something about higher order, so you can check that out. And the viscous part will looking like this. You have the response on the hydrostatic part will look like this, and for the shearing part like that. You can actually rewrite it like this if you want. And this is how you usually do it when you make a mathematical model out of the Maxwell model. And the full one, when you put together, then the elastic and the viscous part will look like this. One thing that can be interesting to have in the model is incompressibility, especially when you work with steel and so on, and rubber is another one. Then you have to put the eta 1 and eta 3 in this. It looks like this. It should be 3 times 2 eta 2. Then you will have an incompressible model. So this is how we can more generalize this one-dimensional model that you have into full tensor model for putting this indices on and putting on tensor relation instead of just using one-dimensional things. Another interesting viscous model is this Kelvin model. It's also usually something that you see in the first courses in solid mechanics. It works like this. You have instead of having a serial coupling, you have a parallel coupling between a spring and a dashpot, like this. Which, when you load the system, will give you this response. You put on the load, but as you have the dashpot in the system, you will have a time-dependent response on that one. So it will be looking like this more or less until you will slowly increase the strains in the system. And it looks like this. You have an elastic part and a viscous part. But now you consider the stresses split. You have the elastic and the viscous stresses, but here you say that the elastic strains and the viscous strains are exactly the same. And the model looks like this. And this one you can directly evaluate. You just isolate the strains in the system. You have to put in the exponential function like this. Then you have the elastic, the strain response of the strain in the system. If you know this eta, then you can find it directly in one dimension. It's straightforward. But you can also generalize it to have a full tensor model instead. So then you, in the same manner, you split the stresses in the system, but the strains you keep together. It's the same. And in tensor form, you have that the elastic stresses are dependent on the strain tensor, and also that the viscous one is dependent on the strain rate tensor. So it's a time, you have a differentiation on time there, change of time. So in the same analogical way that we had in the first one, we divided with alpha 1, alpha 2, alpha 3. And just to find this constant, alpha 1 and alpha 2, alpha 3 is put to 0. We have this relation. And then we have found the elastic stress response for the system. And now you see you can write it with this shear modulus and Poisson ratio. And then you have the volumetric change and the shear part. And the same way you do with the viscous part, now using this beta instead, you will find beta 1, beta 2, beta 3, and the viscous part will look like this. And you have also there division into volumetric and deviatoric shear part. And this is flow connected to the rate, strain rate in the system. So in the end, you can find here that you can write this equation also for the volumetric response, this viscous response, like this. Just put everything together. So you just go through the calculation, and in the book, I think it's the best way to, if you have some questions here about this one. Okay, the last part, hypoelasticity. It's the more advanced model. It's written in rate form. So it's dependent on the strain rate of the system. You have, it's also the stress that you have in the system, but also the strain rate that you have. That will determine the response in the end. This is important. And here you have that the stress rate, how the stresses are changed when you load, is one important thing, and also these strains. You have this relation that you have to work with. And this is a very good model if you have material that respond differently, for example, with unloading and loading, because you can go in different directions depending on. And it's very useful, especially for concrete and soil. It's very common that you have a hypoelastic approach. So this is the Hooke's law written in incremental form, because you're working with rates instead of stresses and strains that you have in other models. So then you find the stress rate. You have a relation there with this lambda times the strain rate for the volumetric part. This is the trace of your strain tensor. And you also have the Kronecker delta there. And the deviatoric part, shearing part, is connected with 2 times mu and the strain tensor. So this is the volumetric and the deviatoric part of the model, an incremental form. It's a very good way actually, because when you work with numerical simulation, you always take small time steps. For example, if you have a nonlinear response in your system, and then this is a good model actually to have for your responses. And something that is quite useful with this type of model is you see that you have softening in the elastic response. For example, this point here says that you have a failure of your model, because this is the maximum stress. And then you have what we call softening response, because you increase the strain, but the stresses are lowering. I would say it's a quite complicated model if you're not used to all this description with tensors and so on, but just read it through so you get a little bit familiar with the hypoelasticity model. So you have a full description there in chapter 7 in the book. So, do we have any questions so far? I will. Have you seen? Have everyone access to this frontal room? So I have put on. You know that I put out an assignment, the first assignment there. So it's for just more or less checking the tensor properties of U. No, but it's a warm-up lecture more or less. If you have any questions, just ask me. Try to work together. It's very good with this type of thing. I will not put out anything this time. I will wait till next time, because then we will have a break in the course for almost a month. I think it's good, because I will put out a new exercise that you have to work with, and it's better than just having lectures and put on more material for you, that you can concentrate on solving these problems before we go on in the course. So next time we will go into closer to this plasticity part and the failure modeling and so on. And then I will put out an exercise covering both elasticity and that part. So if you don't have any question, you can send an email or something if something comes up. Good luck with the course.